Welcome back, everybody. Today's video, we're going to be talking about operators, eigenfunctions, and eigenvalues. All of these are going to be used in your quantum chemistry topics, especially throughout your physical chemistry courses here. So let's dive into what these actually mean. Here we have this notation, where we have this a term, or f of x, and this lambda in front of the f of x. Let's define what each of these things actually mean. This a, with our little notation on top of it, is our operator. This is also known as a transformation, and you'll see it a lot within this specific course. You may also see it in linear algebra as well, and these all correspond to operators and transformations on eigenvectors. So the a with our notation or a caret sign is our operator or a transformation that we're making onto our function here. Where f of x is not just any ordinary function, this is actually going to be known as our eigenfunction. Where if this statement is true above, our operator acting on our eigenfunction give us this lambda times our eigenfunction, then this will be known as an eigenfunction. This is a requirement, this specific kind of function. Then lambda, like I mentioned here, is going to be our eigenvalue. All of these are very important. Operators are our transformations that we're acting upon our eigenfunction to give us our eigenvalue. Another way of wording that, or another way of wording this equation above, is that our operator extracts information, and our information is that lambda value from our eigenfunction. This information will actually correspond to a lot of observables that we'll view within wave functions in quantum mechanics. So this is a very important equation, especially how we get energy out of our wave functions, or how we get position or momenta, or average position and average momenta, depending on what we're actually looking at for our quantum chemistry classes in physical chemistry. Please show your support for this channel by liking and subscribing, as all I want to do is help support students on their learning journey. Now let's move on to some practice problems. Let's show that f of x is equal to e to the 2x is an eigenfunction of the operator d over dx, or our derivative with respect to x. What is the corresponding eigenvalue? So here we have our function that we're testing, f of x is equal to e to the 2x, and our operator is going to be d over dx, or our first derivative with respect to x. Now we remember from before on the previous slide that we have a f of x is equal to lambda f of x. F of x will only be an eigenfunction of our operator if we get it into this form, where after the transformation is applied, we retain our eigenfunction and have a constant out in front. So let's apply our operator onto our function. So here we have a acting upon e of 2x, or we're just going to be taking the first derivative. Or in a future video, we'll cover doing derivatives of special functions such as exponential functions. But the derivative of e to the 2x will first off retain our e to the 2x. That's always true with exponential functions with our variable in the power. Then we'll take the derivative of the power itself, d over dx, of just 2x. And we know from the power rule, we just end up getting 2 times e to the 2x. So here we have our operator acting upon our function. And we can see we can actually extract our function out, so f of x, and then our 2 is actually the value in front of it, which is corresponding to our lambda. So yes, this is an eigenfunction, and our corresponding eigenvalue is that lambda is equal to 2. Now for this generic example, this doesn't mean anything specifically, but if this operator was trying to extract position, momenta, energy on our wave functions of model systems, then we can actually extract those specific quantities using those operators on our functions. Let's move on to another practice. Here, we're going to check to see if f of x is equal to sine of 2x is an eigenfunction of our operator A, where this is actually going to be related to some sort of quantum mechanic operator. This is related to our momentum operator, where you see a little p with our caret sign above it. So first we have our operator, which we're going to do A of f of x, where we're going to apply our operator, negative I, h all over 2 pi, d over dx, acting upon our function sine of 2x. And if we actually apply this transformation, we have negative I h over 2 pi. The derivative of any sort of sine term, we'll have to take the derivative of the inside quantity. So we're going to take the derivative of d over dx of 2x, just like from before with the exponential function. And the derivative of a sine function ends up giving us a cosine function with the same quantity on the inside. And so that we can see that the full transformation is negative I times h all over 2 pi, where h is going to be Planck's constant from back in Gen Chem 1. But here we're just going to use it as a constant. And the derivative of 2x as before is 2 times cosine of 2x. And we can see that our final transformation is negative I over h all over pi times cosine of 2x. We see that we did not retain our f of x function. It is not equal to any sort of lambda value times sine of 2x. So this is not an eigenfunction. And that's exactly how you prove that it's not an eigenfunction, by seeing if you actually retain it with a lambda value in front of it. You may have to act your operator upon your eigenfunction and extract your eigenvalue if it is an eigenfunction, or just prove it's not an eigenfunction like we did here. So let's go through one last practice. So here, we're going to show that our function f of x of y now, where we have a cosine of ax times cosine of by, is an eigenfunction of our operator here, where these are just partial derivatives of our specific functions. And to explain that, this is what you would actually do. So here is our partial derivative with respect to x of our one quantity, and we're taking it of x plus y. What you'll end up doing is that normally x and y are both variables. But when you're taking the partial derivative with respect to x, you're to treat y like a constant. So the partial derivative of x plus y is just going to be 1. The y is a constant, so that'll go to 0. But the derivative of x is just going to be 1. So let's do the same thing for one more practice. The partial derivative with respect to y is equal to x times y squared plus y plus x. And so here, we're going to treat x as like a constant, and our y's are going to be our variables. So the partial derivative of xy squared plus y plus x is going to be 2xy plus 1. Because the x term will go to 0 because it's a constant, our y term will go to 1, and our xy squared will be 2xy because that power rule with our y squared. So that's how we actually use partial derivatives. Now when we apply it on our trig functions, the derivative of our cosine term is just going to be negative sine. And then the derivative of our sine term from the previous slide, or the previous problem, is just going to be cosine of ax. And this will be proved in a later video, for fun, by using Taylor expansions, which we'll talk about later. So using that, we can actually end up solving this problem. So first, we need to act our operator upon our f of x function. We're going to act our operators upon our wave functions, where it's going to be the second partial derivative with respect to x, plus our second partial derivative with respect to y, acting upon our wave function or function here, cosine of ax times cosine of by. Just like these operators, we need to actually distribute our operator onto our function. So what we will end up doing is the second partial derivative, and we should have 2's down here on the bottom. Hopefully you catch that mistake when I first made it. But we have the second partial derivative acting upon our function, cosine of ax, cosine of by, plus our partial derivative with respect to y, the second partial derivative of cosine of ax cosine of by. So now let's take the first derivative of each before we move on to the second derivative. So the first derivative of cosine of ax, because our cosine of by is going to be constant for the first one. So we're going to go to the first derivative now. It's going to be negative sine of ax cosine of by. And we have to remember our a term is coming out as well. So it's going to be actually negative ax, or negative sine of ax. Now we're going to do the same thing for our partial derivative with respect to y, where now we're going to have a negative b cosine ax sine now of by. And now if we take the derivative once more of each term, we're going to write this out in green. We're going to see that we're going to actually have negative a squared of cosine ax cosine of by, because by hasn't, or cosine by hasn't changed, plus negative b squared of cosine ax cosine by. And we can see that our cosine ax cosine of by is in both terms, so we can factor that out, where we're going to have a negative a squared minus b squared times r cosine ax cosine by. And this is the same thing as saying lambda times the original function f of x, where lambda is now equal to our negative a squared minus b squared. So let's make that a note up here. Lambda is going to be, you could also say minus a squared plus b squared, same thing. But that is your eigenvalue corresponding to that transformation. Please comment below something you have learned through this video, and please comment also any questions you may have about any of these topics. Have a great day.